So, hello, my name is Lucy, and I'm together with Tatiana, and we wrote a paper to be here today. We are from the Linköping University in Sweden, and we also cooperate with Market, which is the ANSP for Sweden. Our paper is about testing applicability of point merge systems for Göteborg Landvetter Airport. Um, so the paper is structured in two parts. The motivation for it is that many statistics show that most inefficiencies happens around airports, and we would like to capture where and how that happens. So we try to identify the areas for improvement, and for that we choose the Göteborg Landvetter Airport this time, and we analyze separate traffic flows to see which one behaves bad and which one behaves nice. That's the first part. And the second part, Henrik will talk about it later. We try to suggest how to redesign arrival procedures for Göteborg Landvetter Airport. We propose a point merge solution. We simulate the trajectories through this proposed point merge system, and we try to evaluate how that works. So I talked about point merge. It might be known concept for many, but I will go quickly through it as well. So it's arrival procedure, which was developed by the Eurocontrol Experimental Center in 2006, and it's currently implemented on about 40 airports worldwide, and it's developed to reduce delays and on busy airports. And one of the aims is to help to simplify controllers' tasks by reducing the communication and workload. You can see the example design on the picture which I borrowed. It's the concept about predefined paths, so there is sequencing collects from each direction and one merge point. The blue and orange sequencing collects works as so the flights follow the sequencing collects, and when they are supposed to turn to the main merge point, and depending on how long they fly, it should help to organize them in a successful sequence or in the desired sequence. So as I said, for this analysis, we chose the Göteborg Landvetter Airport, which is the second largest airport in Sweden. It has about 40,000 movements each year. And in the European measures, it's a mid-sized airport. It has only one runway, which is shared with both arrivals and departures. And we chose this airport because we know that they plan redesign or reconstruction of the arrival procedures. And they plan to increase the capacity of the airport, which is currently 6 million passengers annually, and they want to increase it up to 15 million passengers by 2040. So for that, we use historical flight data from the Open Sky Network. We extracted arrival trajectories for Göteborg Landvetter Airport of the year 2019, which was the busy season, but to reach the same level. We have data divided into 6 clusters based on the entry to TMA to represent the traffic flows. And for the first part, where we evaluate the current operations, we use this month of the year, which was April. And for the proposal of the point merge system, we used the busiest day of the month, which was the 10th of April, and about 90 aircraft came during the day. So we evaluate with our evaluation framework. I presented it many times before, so I will just go quickly through it, and if there are any questions, you can ask me later. So we evaluate the vertical efficiency with time from level, which is the time which aircraft spent on levels, and vertical deviation from the reference profile, which is the actual vertical profile from the continuous descent profile. Horizontal efficiency, horizontal spread, which is the percentage of airspace used for the arrivals, and distance flown in TMA, and fuel consumption for environmental efficiency. We also evaluate efficiency of metering and spacing. For that, we use minimum time to final, which is the best performer's time to final in each discrete space in TMA. Spacing deviation, which is the spacing error in between consecutive aircraft. Throughput is what is the minimum time, how many aircraft share the same minimum to final different time windows, and sequencing effort, which is how much effort is the controllers to optimize the aircraft to the desired sequence. We also calculate time efficiency. We calculate time in TMA, additional time, which is the difference between time in TMA and the minimum time to final. And we also decide to calculate the ASMA additional time standardized to see what is the difference in between the standardized ASMA additional time and our approach. And we also describe the point merge with two metrics. One is point merge usage. It's simply how many aircraft from the full set use the point merge system. And point merge utilization is what is the proportion of the sequencing legs used by the aircraft. You can see that the blue aircraft used the sequencing legs on about 80%, and the green used about 60% of the sequencing legs. So this is the evaluation of the current procedures at the airport. I show minimum time to final heat maps for 3 clusters, cluster 1, 2, and 6. So the average horizontal spread is about 13%, but it's 36% for cluster 2, which might be because of the asymmetrical shape of the TMA. And maximum values of the minimum time to final is the highest for cluster 2 as well, which might be the same reason. But in the next slide, we have spacing deviation evolution curves and sequencing effort on bottom. And we have cluster 2 and cluster 6. So cluster 6 is example of, cluster 6 looks similarly as all the other clusters. The shape of the spacing deviation, it's quite linear. And we can see in cluster 2, there is high dispersion of the evolution curves, around 500 seconds to final, which indicates some kind of a control error or control inefficiencies. So maybe the highest maximum value of minimum time to final wasn't only the longest path. And sequencing effort curves or sequencing effort follows the same shape with the peak and 500 seconds to final as well. And we can see it's at least 2 times higher for cluster 2 than for cluster 6. So much more effort from the air traffic controllers had to be used for organizing the aircraft in cluster 2. So in the top picture, there is a evaluation of time on level metrics for each of our 6 clusters. The cluster 2 has high dispersion of the values, maybe because of the inefficiencies I mentioned before. And we can see what is interesting for cluster 4, it has the highest time on levels in average. We can see in the green table that cluster 4 there is only 5 aircraft in cluster 4, so this requires further exploration. We think it might be some weather conditions. And in the bottom picture, there we show ASMA additional time and our additional time based on minimum time to final for 3 clusters. We show only 3 clusters because we couldn't calculate the reference transit time of ASMA for the other 3 clusters because there wasn't enough flights in the datasets. And the results show similar values. And we are happy because we think it validates our approach nicely. And yeah, that was mostly about the validation. And I think I will open the floor for Henrik.
Thank you, Lucy. So now when Lucy has shown the current performance in the airport in 2019, I will take over and show an application of how we tested the PM point merge applicability at the airport. But I should probably first start by saying that this design is not designed or proposed by us within the research group. It's rather a design that has been used and proposed within an ongoing airspace redesign and procedure redesign project within the airport at LFV. So we are basically using one of their versions of the PM design that has been used. And we will use a previously developed optimization framework for testing this applicability. So this part 2 is not about developing the optimization from framework, but rather applying it to the point merge design and to this airport. So, and how did we use the OpenSky network data then for this? Well, we applied this to a busy hour scenario where this data is being used. So you can see this picture here, which is the proposed design that we used. So it basically has 2 separated legs along which aircraft are allowed to descend, so they are not overlapping. So they can perform a continuous descent along the arc and don't need to stay on level flight. And also ourselves, we took the decision, or we interpreted how to use the design in practice. So we set 3 different like arc entry points each for each arc, where the aircraft can join the sequencing legs. And in order to use it for the optimization and to create the different route options that aircraft can use, we also discretized the sequencing legs. So basically we added intermediate additional points between the existing waypoints along the sequencing legs. So basically there are 2 merge points, 1 for each arc, and then after that the aircraft will merge in the intermediate approach fix before continuing along the final approach. So from the OpenSky data network, we obtained both data for arrivals and for departures. So for the arrivals, we were interested, or we obtained the aircraft type for the trajectories, the entry time into the TMA, the TMA entry coordinates, the TMA entry speed converted to calibrated airspeed, and also the cruise altitude. But also since, as Lucy explained, this is a single runway airport where arrivals and departures share the same runway. So somehow we also need to take into account the departures and how that affects the ability for the arrivals to use it. So for the departures, we obtain the aircraft type and the timestamp of the first recording. So this, you've seen the picture before, but now I will explain the different route options that there are for the aircraft depending on how they join the sequencing legs. So what we did is that we analyzed the trajectories, the actual trajectories, and we assigned them an entry point along the arcs depending on where they arrive into the TMA, basically. So the route is going from the entry point of the TMA to one of the orange waypoints, which one is the closest, and then they will be scheduled along the arcs depending on, well, how much traffic is coming. So for example, if they enter via East 6 or West 6, they will have 16 route options, which means we have actually 2 intermediate waypoints in between the published ones. And if they join via East 3 or West 3, there will be 7 of them, they will go like this. But as you can see, if they enter via East 1 or West 1, they only have the possibility to join the merge point directly. So in that case, we also made it possible or added additional route options for them to join also via East 3 or West 3 if that would be required. In terms of vertical profiles, we use Eurocontrol data. We considered the actual wind and temperature within the atmosphere during this day. For the modeling, we used the total energy model and modeled at a continuous descent at idle thrust. We set up a speed profile. So first matching the entry speed of the aircraft into the TMA, and then some additional constraints of the speed depending on altitude or where they are within the airspace. And of course, we need some separation requirements in order to have a safe operation. So we did that depending on whether it's a medium or heavy category wake turbulence aircraft. So we didn't have any light aircraft in this experiment. And I should say also that we schedule the arrivals only to the intermediate approach fix. So in order to take into account how the synchronization is between the arrivals and departures, we had to estimate the flight time between the intermediate approach fix and the runway threshold. And we also, of course, had a time separation between the arrivals and the departures. So as I said, this is based on a previously developed optimization framework, which has been developed within our research group. So it's based on mixed integer programming. And the goal is to provide the optimal assignment of arrival routes to each aircraft, given the current traffic situations. So we have the optimization framework itself, which is we used with the objective to minimize the fuel consumption, the total fuel consumption of all aircraft. But before doing that, we need to identify which arrival profiles are conflicting. And that is as an input then to the optimization framework itself. We have a couple of different constraints which goes into the optimization framework. So we need to make sure that we assign each aircraft only one arrival profile, and that the conflicting profiles which do not adhere to the time separation requirements cannot be selected simultaneously. And we also need to provide the necessary spacing between the arrivals and departures. And as an output, we will have the optimal assignment of arrival profiles. So for the data set or the experiment that we conducted, we were looking at April 10th, 2019, which was a busy day during this year, with 90 arrivals, 84 medium and 6 heavies, 95 departures, and in total, we had 988 arrival profile options that were constructed for this scenario, which you can see in the figure to the right. And we had about 1,400 different profile pair conflicts that had to be considered within the optimization. To the figure to the left, you can see how the different aircraft actually flew during this day. So basically, the optimization framework should use the different arrival profiles that we have considered that are available to the aircraft and pick the optimal solution. And we also encountered a problem that the ground coverage was quite poor at the airport, so we had to make an estimation on when the aircraft actually took off from the airport. So Some aircraft were detected on the ground, but most of the aircraft were detected at about maybe 1,000, 1,500 feet approximately. So this is the optimized arrival schedule so the top figure shows both departures and arrivals, so the number of movements. So we had a peak at around 7, 8 in the morning. It's UTC, so it's 9 to 10 local time, and another peak at around 4 to 5 in the afternoon UTC. And the figures below show in 6-hour periods how the aircraft were scheduled to take off and to land. So you can see the orange dots represent the arrivals and the blue dots represent the departures. And I think it's visible also for you, but there is for some of the orange dots, there is a short vertical line below them, which is to represent or to indicate when point merge was used, and yeah, basically when sequencing legs were used. So in the rest of the cases, the aircraft could go directly from the initial point of the sequencing legs to the merge point. So we can see that some aircraft had to use point merge in the early morning, and then there were no aircraft using them, and there were about 3 aircraft there at like 8 o'clock or something, and then some were later on. And I can now see that it should be the third and the fourth should be switched. So it's a mistake by me. Yeah. You have seen the actual routes before in the previous slide, and this was the proposed solution by the optimization framework. So you can see, for example, some flights entering here are going directly to the initial point of the point merge system, and then to the merge point, and then to the intermediate approach fix. And some of them are scheduled to use the point merge. So in terms of the utilization itself of point merge, we have less than 10% of the aircraft using the legs, and none of the aircraft were using up to 80 or 100%. So it was, yeah, as you can see, mostly at maximum at 60%. So not that many aircraft actually using the point merge system for scheduling. So looking at some results on time, distance, and fuel, we observed on average 5% fuel saved per flight, and this is within the TMA itself, so it's not considering the whole flight, but only within the TMA. Time and distance increased by about 10%, and that applies to all clusters that we analyzed. And one cluster had also an increase in the fuel consumption, which is cluster 2 here in this case. But there is quite a large variation on how many aircraft use the different clusters, so it's very difficult to compare the performance in between them. And in terms of the vertical performance, you have the actual vertical profiles in the figure to the left, and the middle is the vertical profiles that we modeled with the total energy model at CDO, idle thrust. And we looked into the vertical deviation, so basically how much the actual profiles deviate from the CDO profiles at the last 10 minutes of flight. So we can see that there are some vertical inefficiencies that affects the fuel consumption. But yeah, for 4 and 5 clusters, there were only 1 flight, so that's the reason why there is only 1 line here. So as sequencing is and spacing, which Lucy has also explained before, we observed similar maximum of time to final. The average time to final increased for the optimized scenario, which is in line with the increase in time in TMA. And we can see for both actual at the top and optimized that the spacing deviation is very dispersed at the 900 seconds to final, because flights are arriving at very different locations within the TMA, and they have a very different duration of flight as well. And we can see that the flights in the optimized scenario is at time 2. Yeah, so we have performed the cluster-wise performance evaluation in the first part, and yeah, evaluated this optimization framework. And we can see that only 10% of the flights were using PM. So probably the systems can be reduced and redesigned for better efficiency. But on the other hand, it's a better organization of the flows. Okay.
Thank you. So I have a first question. Yeah. I think it's very nice that you come with a optimization problem to compare the with and without point merge situation. I'm just wondering, isn't it more fair to do a comparison with on 2 optimization problems, like one with a point merge and one like running exactly the same thing but without the point merge procedure implemented, rather than comparing with a real trajectory? What do you think?
Yeah, of course, we could add additional route options, but on the other hand, we wanted to, since they are thinking about implementing point merge, I guess, LFV is also interested in knowing how does it look like compared to the current operations, and could it be improved? And maybe this can show that.
I'm just saying that would be an extra step to do.
Yeah,
that is just, keep this and just for a more fair comparison to compare with.
Yeah, sure, definitely. Maybe. Then just we need to decide on what would be the other option in terms of procedures and routes and so on.
Just the current one?
Yeah, sure. We can use the current standard arrival routes. That's it's a good idea.
I just have a comment. Thank you very much for the presentation. So over the years, we have been trying to use OpenSky data to do a lot of analysis, try to improve the data. Very rarely we see real impact of this data on what future ATM could be. And this is one of the few projects actually now is in really working with the real NSPs and try to use the data to bring the innovations and bring really the ATM application to the ATM. So really, I want to say thank you very much for showing us this presentation. Really valuable for the OpenSky community, and we are really looking forward to see more use of this data in actual airspace design, for example. Yeah, thank you.
Yeah,